So previously we had seen that the gravitational force is a conservative force field. So obviously you can define a potential energy. And we shall see the very familiar gravitational potential energy. Um, so let's start our discussion near the surface of Earth, where, as you know, the gravitational force is a constant mg. Of course, if you go farther and farther away from Earth, then it's not necessarily this constant force, so we shall talk about that later. So once again, when you define potential energy, you can use the fact that you can add constants to potential energy to set the potential energy to be zero at some reference level. In case of gravitational potential energy, people usually set the potential energy to be zero at sea level, but really this is up to you where you do this. And when you set the potential energy to be zero at sea level, you will find that the gravitational potential energy at some height h above the chosen level is mgh, which is a very familiar formula. Let's see how that works out. So let's say you have a point A and a point B at some vertical height h above A. It doesn't have to be exactly vertically above. It could be displaced horizontally, and of course we shall see that by choosing a convenient path we shall see why that is. So let's set the potential u equal to 0 at the x-axis at this level. You can do this, of course. Now let's find the work done in going from point A to point B. Here you can choose any path you like. So let's choose a convenient one. Let's choose a path like this, such that, on this segment, of course, you have this work done equal to minus mg into dy. The displacement is upwards, and when the mass is moved up like this, the force is downwards, this mg. So you have this negative work done, and along this segment of the path, the work done on this mass by the gravitational field is of course 0. So obviously the work done WAB equal to minus mgh. Notice that this horizontal displacement from initial position does not matter at all. It's only this vertical displacement that comes into play. Now, because this force is conservative, we can write this as a negative of the change in potential. Setting the initial potential to be 0, you have minus ub minus 0 equal to minus mgh, so that ub equal to mgh. This leads us to a nice form for the conservation of mechanical energy in projectile motion. Of course, in projectile motion, the only force acting on the body is this mg minus mg j hat if you select axis like this. And this force being conservative, you have once again this WAB equal to del K, which holds in general. It's the work kinetic energy theorem. But because this work done is by a conservative force, it's equal to the negative of the change in potential. And then because UB equal to mgyb and UA equal to mgya, so rearranging this equation, you have half mva square plus mgya equal to half mvb square plus mgyb. In other words, you have this half mv square plus mgy equal to constant, which is the total energy of the system. So the natural interpretation is that suppose you release a body at point A. While it falls down, the gravitational potential energy keeps decreasing because y keeps decreasing. At the same time, this body speeds up, so the kinetic energy increases in such a manner that their sum, so kinetic energy increases, potential energy decreases, but their sum remains constant. These are formulas you must have used many times in doing calculations. Okay.